Hello and welcome to today's class on kinetics of rigid body. So we are going to be considering this question. The question says the link AB of the robot arm is rotating at 2 radians per second in the counterclockwise direction. The link BC is rotating at 3 radians per second in the clockwise direction, and the link CD is rotating at 4 radians per second in the counterclockwise direction. What is the velocity at the point D? Alright, so I'm going to be showing you a free body diagram of of the diagram. Let's explain some few things from the free body diagram. Now you're given a link, a robot arm with links A to B, B to C, and C to D, and you have to find the velocity at point D. Now to do this, the first thing, we are given the angular velocities. The angular velocity between arm A to B was given as 2 radians per second, and it is in the counterclockwise direction. So this is the anti-clockwise direction against the direction of clock. Okay, whereas the link B to C is moving in the clockwise direction. So this is the clockwise direction with an angular velocity of 3 radians per second, and links C to D is moving also in the anti-clockwise direction with an angular velocity of 4 radians per second. So this is all the directions indicated. Now we are to find the velocity at point D. To do that, between A to B, since point A is fixed, we always start with the point that is fixed. And since point A is fixed and the motion is relative from point A down to point B, which is why you're having angular velocity A to B, is simply because the motion is relative. Okay, so relative motion between A to B, we are going to be having a velocity at the other end from at point B. This velocity is called a relative velocity. Okay, and this velocity must always be in the direction of the motion. So since the AB is moving anti-clockwise in this direction, we have a velocity which is also in the same direction as direction of motion, and this velocity must be at 90 degrees to the arm. So you have this velocity, it must be at 90 degrees to arm AB, so which is something like this, as can be seen here. So this is direction of the relative velocity, VBA. Alright, so the same thing is applicable. Moving down from point B to point C, we have the relative angular speed or angular velocity, which was given in the clockwise direction. And since it's given in the clockwise direction, it means velocity at the other end, which is the relative velocity, must also be in the same direction as the clockwise direction or direction of motion. So you have that speed in the same direction, and it must be at 90 degrees to the arm B to C. So which is why you're seeing this vector, which is why you're seeing this velocity vector pointing downwards here, because it must be in the same direction as the direction of motion, and it must be at 90 degrees to the arm BC. Finally, C to D is rotating at the anti-clockwise direction as indicated here, okay, with this angular speed. Also, at the end, which is at point D, we must also have a relative velocity which is now in the same direction as direction of motion. So since motion is clockwise, our speed will be what? Clockwise, but it must be at 90 degrees to the arm, which is why you have this speed to be this. Okay, now in analyzing kinetics of rigid bodies, or in analyzing motion of rigid bodies, you always start with a point that is fixed. Now, point A is attached to a fixed point, which means we have to start from point A because point A is fixed. So we consider the rotation of point A, the pure rotation of point A. So what we'll do is simply draw the free body diagram of only arm A to arm B, leaving this part aside. Okay, so we only consider arm A to arm B, leaving this part aside. So I will take you now to the free body diagram. Alright, welcome back. So we consider now the rotation of only arm A to B. Okay, let me pull back the diagram. We are simply considering only the rotation of arm A down to B. Okay, so remember, arm AB is moving with an angular speed of 2 radians per second in the counterclockwise direction. So we have an angular speed here, omega AB, of 2 radians per second in a counterclockwise direction. Then I explained earlier that if we have this, then at this other end, we are going to be having a relative velocity between A to B, which must be in the direction of motion, and it must be at 90 degrees to this arm AB. So we simply have a relative velocity which must be at 90 degrees to this arm, as can be seen. This is 90 degrees, and then this is simply VAB, relative velocity between arm A to arm B. Not forgetting, let's pull back the original diagram. Now, in the original diagram, distance between arm A to B was given as 300 millimeters. So we convert that to meters, that becomes 0.3 meters. Simply dividing 300 by 1000. So the distance between arm A to arm B is simply given as 0.3 in meters. Okay, now this relative velocity VAB is given mathematically as VB minus VA, always the velocity at the extreme end minus the initial velocity. So the aim is to obtain velocity at point B. That's the main aim. Okay, the aim is to obtain velocity at point B. Okay, so using the informations of velocity at A and that of the relative velocity, we can obtain velocity at point B. So we simply make V be subject of the formula. This means velocity at point B equals the relative velocity between arm A to B plus, if negative sign cross an equal sign, it becomes positive. So you have plus VA. Now, like I said, when analyzing motion of rigid bodies, you always start from the fixed point. Since point A is fixed, it means that velocity at point A is equal to 0. Since that point is fixed, then VA is 0. So this simply implies that VB is actually equal to the relative speed VA to B, since VA is 0. So this is our equation, and this is how we find velocity at point B. Okay, now where VB itself, VB relative to A itself is always given as the radius along AB. So radius of arm AB multiplied by the angular speed of arm AB. That's how you find the relative speed between arm A to B. Okay, so the relative speed VAB is now equal to the radius arm gave us here to be 0.3 meters. That's distance between A to B. So you have 0.3 multiplying by the angular speed. Relative angular speed now was given as 2 radians per second. So multiply by 2. So this simply implies that relative speed VAB or VBA is simply 0.3 times 2. That gives us 0.6 meters per second. So this is now the speed relative from point A down to point B. Now, if you know this speed, that simply means that the velocity at point B is also what? Because VB is equal to the relative speed. So it means velocity at point B is also 0.6 meters per second. Now we have velocity at point B. We are done now analyzing the motion or pure rotation of arm A, B. Now we consider rotation of arm B and C. We're using the same idea. So our aim now is to find the speed at point C. So you simply consider now the motion of arm B down to C. Okay. So distance between point B to C was given as 250 millimeters, which we can convert to meters by dividing this value with 1000. That simply gives us 0.25. So the distance between this arm is 0.25 in meters. Now, as explained earlier, the relative speed, which is VBC, is always given as VC minus VB. So it's always the velocity of the arm in front minus velocity of the arm behind. That becomes the relative speed. Okay, now the aim at this point is to find velocity at point C. This simply implies that velocity at point C becomes equal to, remember, VBC, sending VB over to this side, it becomes plus. So we have plus VB. So this becomes our velocity vector at point C. Okay, we now need to find the value of the relative speed between B and C. Again, VBC, so keeping this equation aside for VC, VBC itself is equal to the radius arm between B to C multiplied by the angular speed between B to C. So this simply means VBC equal to the radius arm is 0.25. So you have 0.25 multiplied by the angular speed, and the angular speed was given as 3 radians per second, so multiplied by 3. So this simply implies that the relative velocity between B and C is equal to 0.25 multiplied by 3, that gives us 0.75 in meters per second. Now if you know this, simply plug into this equation and you will obtain the value of the velocity vector at point C. Alright, so this simply implies that velocity at C is equal to, remember, VBC plus VB, and VBC gave us 0.75, so we have 0.75 plus, earlier we solved for VB and we obtained velocity at B to be equal to 0.6. Okay, we obtain the velocity at B to be equal to 0.6. So plugging that into this equation, you are simply going to have that velocity at C, okay, is equal to 0.75 plus 0.6. So this simply implies that velocity at point C is equal to, that gives us 1.35 meters per second. Now, if we know the velocity at point C, we still carry out the same analysis. Now, we are going to be considering motion between C to D. So we consider the pure rotation of arm C to D, carrying out the same analysis. That will help us to find the velocity at point D. Okay, so we are considering now pure rotation of arm C to D. So now we consider the motion of arm CD. As can be seen, this is the motion of arm CD. Remember, the angular speed was given in the anti-clockwise direction and the value is 4 radians per second. So you simply have angular speed in the anti-clockwise direction. So omega CD is 4 radians per second. And I said if you have the angular velocity in the clockwise direction, then you must have a velocity vector, okay, which must act in the same direction as motion but must be at 90 degrees to the arm. So since this arm is purely horizontal, it means at 90 degrees we are going to be having a straight line, okay, velocity vector. So this is called velocity of C to D, which is relative velocity from point C down to point D. Not also forgetting that the radius arm not also forgetting that the radius arm of C to D was given as 250 millimeters, which will convert to meters by dividing this value with 1000. So the radius arm simply will be 0.25 in meters, and you have this. Okay, now remember that the relative speed VCD is going to be VD minus VC, okay, and the aim is to find the velocity at point D. So we simply send VC over here. This simply implies that velocity at D is equal to the relative speed VCD plus VC. Okay, so you keep this equation aside. Now we find relative speed between C and D, and that's simply the radius arm of CD multiplied by the angular speed of CD, and this is equal to radius arm of CD gave us 0.25, so we have 0.25 multiplied the angular speed of that motion is 4, so multiply by 4, and this simply implies that the relative speed between C and D is equal to, let's obtain that multiple. 0.25 multiplied by 4 gives us 1 meters per second. So if this is the relative speed, then plug it into this equation to find the value of velocity at point D. So this means that velocity at point D is equal to VCD is 1, so you have 1 plus velocity at point C, that gives us 1.35, so plus 1.35, and this is equal to 2.35 meters per second. Okay, so this is the velocity at point D. Therefore, velocity at point D is simply 2.35 meters per second. Alright guys, so that's it for that question. In the next video, I will see you with more examples on kinetics of rigid bodies. Thanks.